Let's try this idea out again as we take a look here at example number 2. Let's suppose we have the following scenario. Car A is going to be traveling west at 50 miles per hour along a road, while car B is traveling north at 60 miles per hour. All right, immediately I'm going to go ahead and I'm going to start sketching out a little moving picture here. First, I could see that I could imagine car A traveling west. Well, if I imagine that car A is going to be right here, I know that car A is in motion, and it's moving in this particular direction. It's moving west, maybe towards an intersection right here. So I'll even go ahead and I'll label this part as my intersection. Okay? Now, I can also tell you exactly how quickly the car is changing its position, right? I know the speed of the car. So I can actually write over here that the speed of car A is actually going to be equal to 50 miles per hour. Now I'm going to go ahead here and note just something else here that's going to be happening here in this picture. So I'm going to go ahead and just label this here with a DADT. So down here I can see that I have car B and that this car is moving north. And again, I know the speed at which car B happens to be moving. I know that dB/dt happens to be 60 miles per hour. Okay, so this is at least kind of the starting scenario. I can imagine right now where exactly these cars are and where exactly they're moving. Now, a couple things that I should note that are going to be changing in this picture automatically. I could ask right now, what is going to be the total distance from the intersection to car A? And, well, I mean, I guess the answer to that is, I don't really know, right? I mean, the car's moving towards this, so it's constantly changing. Why don't we go ahead and give this side here, though, this length of this side a name. Let's call it little a. And this side here, I don't know how long it's going to be, so let's call that little b. I recognize these things these are things that are changing within the picture, and so I'll label them with different values. Now, what's going to be kind of interesting here is that you'll see that I chose to write my speed of my car and the speed of car A and car B with this little b and this little a. Because notice that if the car is moving at 50 miles an hour, I'm also kind of telling you how quickly this line segment is moving. Right? That is, the line segment connecting the intersection to car A is kind of moving or closing, it's kind of shrinking at a speed of 50 miles per hour, and same thing here with side length B. Okay, so that is all information just to kind of tackle the first sentence. Now, we've already kind of seen that both cars are going to be headed for the intersection of these two roads. And the real question we have here is at what rate are the cars approaching each other? Okay, so the cars are approaching each other. If I wanted to measure, say, the distance between the cars, I could measure the distance kind of like right here, right? This would be how close the cars are together, because if I want to measure the distance, I would just measure along this diagonal, this straight line here. Now, I don't know how close the cars are. Let's call this side here C. And I can definitely tell that this side here is going to be shrinking, right? I mean, as the cars move forward and towards the intersection, the distance between them is going to shrink. But the real question here then is, what is the speed at which this side is shrinking, right? So what is dc dt? How quickly is that side growing or shrinking? Well, what I'll see here is that when I come to this stopped picture, I'm going to recognize that I have all of the same pieces in play, right? I still have A, I still have C, I still have B. I still have my cars, but now they've kind of been locked into a particular position. So I have car A and car B in these spots. But I'm choosing to stop at the moment when car A is 0.3 miles from the intersection. So that would mean that over here, I'm going to stop when this side length here is 0.3. And I'm also going to stop when the side length of B is going to be 0.4. Now, of course, these are if these values are given to me, I can find out a lot of other information here in the picture. I could start to find something like the area of the corresponding triangle that's formed here. I could find this missing side length of C. I could find a whole bunch of different things. Of course, the only thing that I'm really going to focus on grabbing right now is maybe just this value of C, since it seems pretty easy. You may recognize this here as a common Pythagorean triple. This would actually be a 3, 4, 5 triangle. And if you weren't sure of that or you didn't see that, you could of course always just use Pythagorean theorem to help you, since you do have a nice little right triangle here. Okay, so again, this is just the scenario. I haven't even got to solving the question yet. But once I do all this legwork, solving the question is pretty easy. Let's take a look. I need to come up with some equation that's going to relate the different variables that I have within my picture. So I have an A for the length of this side in car A. I have a B for the length of this side in car B. And I have the distance in between them that I've called C. Any formula that I could use that kind of relates all of these different values together? Oh, well, how about something like this? C squared is equal to A squared plus B squared. Couldn't I just use Pythagorean theorem? I mean, I know that that's true in this scenario because I have a nice little right triangle here, right? So again, step one, I'm looking at the moving picture here. And so I'm saying, I know that A squared plus B squared is equal to C squared. Great. Now I can move on to step two. Again, this is also a blue step where I'm going to go ahead and take the derivative of both sides with respect to my variable of t, my variable of time. I know that all these values change over time. So if I take the derivative of this side, notice I'm going to get stuff squared, so its derivative is 2 stuff to the first times the derivative of the stuff. On the other side, I'm going to get kind of the same thing. 2 stuff to the first times the derivative of the stuff. And then 2 stuff to the first times the derivative of the stuff. Notice that since, again, none of the variables in here are t's, I have to use the chain rule to calculate the derivative for all of these things. Well, now I can go ahead and I can move on here to step number 3, which is I can state that if I'm going to pause this picture, I'm going to stop the movie at a particular moment in time and take some measurements, I can go ahead and plug in those measurements now into my formula. So let's see. I'm interested in finding dc dt in the question. So as long as I can replace the value of c, a, b, dA dt, and dB dt, I'm going to be in business. So let's see what we come up with. I know that at the moment that I stop, this value of c is going to be 0.5. I don't know what the value of dc dt is, but that's okay because that's what I'm trying to look for in the question. I know that the value of a is going to be 0.3 when I stop. I know that dA dt was equivalent to 50. I know that the value of b when I stop is 0.4, and the value of dB dt is again 60. So it looks like I have everything that I need here. I just need to simplify stuff down as much as possible. Notice over here, this is really just 2 times a half, so that's just going to turn into a 1, so I'm just going to have dc dt. Over here, let's see, I'm going to get 100, and then 30% of 100 is going to be 30. Over here, I'm going to get, let's see, 120 times 0.4. I think that's going to come out as 48. And so then if I kind of put all of this together, I get dc dt is going to be equal to 78. Now I just want to go ahead and put some units on this, which again should be really, really easy to do because my units are already given right here. I have c over t. If t stands for time, I just want to go back to this question and think about how have I been measuring time? And, it looks like I've been measuring it in hours. Okay. How have I been measuring the value of c, or a, or b, right? When I say this is 0.5, this is 0.5 what? 0.5 feet, 0.5 meters, 0.5 kilometers? What are we dealing with? Oh, looks like miles. So notice here I'm going to have 78 miles per hour. And so, of course, if you wanted to write that with the more common abbreviation of mph, you're more than welcome to do so. So this is the speed at which the cars are approaching each other at this specific moment in time.